Today, continuing with our discussion of mechanisms kinematics, we're going to investigate today the topic of screw drives. As you probably already understand, threads and screws serve a number of purposes. One, of course, act as fasteners. Another, of course, is to use to transmit power, which is a very important aspect, and that's the kind of thing that we use in kinematics. So, to look at this then, look at a thread form. Typical thread as drafters, you've seen this before. But identifying the important parts for us would be the dimension D, which is the pitch diameter of the thread. And again, just like belts and chains and other things that rotate, we have to have a point that's halfway between the top of the form and the bottom of the form in order to transfer the maximum power. The other important thing here too, just as we saw in chains, is a pitch, which is the distance between two adjacent threads. Now looking at this then, we have a couple of situations where we can have thread forms that are multiple on the same cylinder. So therefore we could have a single thread form, which means this is only one continuous helix down the thread. We can have two or three, all on the same thread form. So it's a possibility to add more than one form, so therefore increasing the strength of the screw thread. So in that relationship then, if L equals the distance between individual threads, and N equals how many threads you have on the screw, times P, the pitch, then we can find a relationship between the strengths of these threads. Now, pitch is, if you want to put it into a formula, is equal to 1 over the number of threads per inch. So therefore, if you have a multiple thread, then you're going to have a longer pitch. So now, once you realize these two important characteristics, then let's take a look at a couple of things that we should know about threads as they're used for transmitting power. Now the types of movement that we can have rotational or axial movement. The rotational of the thread would be this movement here, and axial would be along the axis. So as that moves, and if there's a stationary point, as that turns, then you're getting axial and rotational movement. We can have this movement either go clockwise or counterclockwise. Usually this is to tighten, and this is to loosen. So depending upon what kind of thread you have, then tightening and loosening, you have what are called left-handed or right-handed threads. Now, the translation here of threads, which was the degree of freedom that there is between the two parts, usually, and it's explained here, say between a nut and a screw. You can have where both these pieces move. So the nut moves and the screw rotates. Or you can have these other examples. Screw moves and the nut rotates. The screw moves and rotates, and the nut moves and rotates. It all depends upon what kind of an application you're using here. You'll see the relevance here as you look at the book. Now finally, the conventional notation for this is that part A is the piece that rotates, okay? And part B is the piece that's attached, and usually that is stationary. So if you try to look at relationships between the two, then you have to look at relationships to one of these types. So that all comes to individual problems, and then as you look at individual problems, you'll have to identify what the relationship is. So hopefully you can understand that a little bit. Now the kinematics, basically what we're trying to do, again, is to find out what the velocity is going to be of the thread axially, in other words, how fast it moves along its axis. And to do that, then we need to take into consideration the lead, which is the distance between a single form. Take into consideration the axial distance that it's going to have to move, and then taking into consideration the number of revolutions that it's going to make. So with this, you can determine lead, or if you have to determine the axial distance, you can use this formula here. Depending on what you're given and then what you need to find, use these formulas. And so now the linear velocity here, or the tangential velocity in this case here, as v relates to a, would be the lead times the rotational velocity. Very similar formula to what we've had in other of these mechanisms. And so therefore we're applying the same principles, but this time we're using the thread form as part of the problem. So here is your advancing speed axially, usually in inches per minute or feet per minute, whatever it happens to be. It's movement going in a straight line. The lead is in inches per revolution. In other words, the lead moves per each revolution, and lead could be the same as pitch if it's a single thread. And then W is the number of revolutions per minute. So that's the speed, how fast it's going around. So these are the basic formulas for screw drives. And once you get into a problem situation, you'll be able to adapt and see what you're given and how to solve those problems. So with this information in the book, hopefully you'll be able to do the following problems and make sure that you keep the book and the class notes handy. All right, thank you very much, and let's go and do some problems.